So all Americans who were able to get away on the 4th of July, thank you for coming. Okay, so each talk is, I'll remind the speakers, each talk is 45 minutes. That includes questions, so please, the chairman will try to keep you to 40 minutes plus 5 minutes of questions. Okay, well, our first speaker, I'm the chairman of the first session, so I'll introduce our first speaker, Jean Eisenstaedt, and he's an expert on, an authority on the history and the development of general relativity, and particularly one of the few people in the world who's really studied the development of the theory after Einstein wrote it down. There's been a lot of work on Einstein himself. But now we're going to hear from Jean, who's at the Observatoire de Paris, on why was the acceptance of black holes as physical objects so difficult.
Thank you for the invitation. Yes. Okay, I thought. Okay. So. I remember that on my honeymoon in 1913, I had in my luggage some reprints of Einstein's papers, which absorbed my attention for hours, much to the annoyance of my bride. These papers seemed to me fascinating, but difficult and almost frightening. When I met Einstein in Berlin in 1915, the theory was much improved and crowned by the explanation of the anomaly of the perihelion of Mercury, discovered by Leverrier. But I learned it not only from the publications, but from numerous discussions with Einstein, which had the effect that I decided never to attempt any work of this field, in this field. The foundation of general relativity appeared to me then, and still does, the greatest feat of human thinking about nature, the most amazing combination of philosophical penetration, physical intuition, and mathematical skill. But its connection with experience were slender. It appealed to me like a great work of art, to be enjoyed and admired from a distance. This was what Max Born said in 1955. Einstein was dead some months before, and it was in Bern for the 15 years of the special 50 years anniversary of the special theory of relativity, and it was questioned. But at the time, you know, from 1915 to the 60s, the situation was really difficult, you know. I worked much on this, and I called it the low watermark of general relativity, the desert crossing. Because nobody, like Born was a friend of Einstein. He was a great physicist, and you know, it was really difficult to work on relativity. You know that if you read something by Thorne, for example, but anyone who worked in relativity, and well, I began working in the 1960s, you know, it was not the way to be taken, but quantum. Okay, that was much more. And the first thing is experience what Born told you. And so it was a really difficult time. And I will stay in what I am to tell you on this period, because, you know, general relativity was a difficult theory. And we have to understand why it was such a difficult problem for the expert. Now it's not anymore for you, but it was for all who worked at the time. Why? Because they were Newtonians, you know. They were Newtonians. And it was really difficult to understand what it means, topology. Nobody worked on topology, or quasi. They didn't know what was topology, only Weil, on some others, but generally. And they didn't want to work on tensors. The British in 1920 said, we don't want to do it. There are quotations about that. And so, you know, and what was important? The three little effects, you know them, perihelion, deviation, deflection, and it was so, you know, nothing. 43 seconds of arc per century for the perihelion. It was ridiculous. And still now, I can tell you, you know, what is the use of general relativity? Only to understand the universe and to get, you know, the distance where you are on the planet. But, well, there are no applications. That's clear, or quasi no applications. And this is the problem of the theory, and it's the way we have to understand it also. What Born said, all was there, you know. But, well, so it was complicated, general relativity. The concepts were complicated. People never, Einstein from time to time, but not always, knew what was important, the proper time, you know. As Molière, you know, in some play, he said, le poumon, proper time, this is the main thing. But, well, it was really difficult to accept, to understand. And we will see in what I will tell you on the Schwarzschild solution, on the Schwarzschild singularity. I will always say the Schwarzschild singularity because it was the way they understood what you call the horizon. It was no thing, the horizon. The horizon came after the 70s. You know, I was young at the time, but I've been raised like that. And I know how difficult it was. And that was the reason, too, why I decided, before I wanted to get into the history of physics. But why on black holes? Because I didn't understand it. People in Paris, but not only in Paris. There were few to understand something. Penrose, Wheeler, and so on. I will not speak about them, you know, but they were understanding. But the Kruskal solution, but it was something ridiculous for people in Paris and elsewhere. They didn't understand, I didn't. And so it was a long way to do it. I did it as an historian, and I was convinced, but not at the first time, okay? And I was not, you have to be understanding for our misunderstanding, okay? But, you know, the Schwarzschild solution, I will speak about that, is the most important one in general relativity. This is clear because, you know, this is a program, but well, I'm not sure to do that. You know, I have so much to tell you. You have to have just a view of it. But the Schwarzschild solution, why it's important? Well, because when you, at the time, made some calculation, it was from the Schwarzschild solution. For the deflection of light, for the perihelion, not for the deviation of line rays. But, well, you know, it was. And concerning the effects, you know, it was only in the 60s that the third effect, the problem of the light rays, the redshift of the light rays, was really detected and convinced relativists. Only in the 60s, you know, by Pound and Ripka. And it was a great time for relativity. There are quotations. Well, I will give you at the end a list of, well, works I've done and where you can read all of that. I have no time for it, okay? And so what we have to do, where is that? Okay, this is Einstein, Born, I read, important, but not only read, you know, I have quotation also from Schwarzschild for the difficulty of the Schwarzschild solution. Well, one more word for the Schwarzschild solution, why it is important, or general relativity too, and why the Schwarzschild singularity is important. You have to put that, to understand that. It's important because it's light and gravitation. It's not anymore, you know, what I call from 1950 to 1965, 50 years of relativity. You know, the neo-Newtonian interpretation, only perturbations were important. I exaggerate, but not so much. You had no complete understanding of the theory. And afterwards, you know, the Schwarzschild singularity, they didn't understand that, but we do now, of course, it's the horizon. It's light and gravitation, where light is, you know, say is infinity, you know, and gravitation is very important. And so it's there that general relativity will express it, okay? The expression of general relativity, it's important masses and great velocities, light, gravitation, great masses. That's the reason why they couldn't understand, because it's the very meaning of the horizon, where everything is at the limit of the theory. But while at the time, they were not interested in some way, only a neo-Newtonian interpretation. And we will go to understand this time, difficult time, okay? This is Schwarzschild, you know, before he died, you know, from Pemphigus. This is Einstein to Schwarzschild. He was really interested because it was just after, well, but... And this is the solution, the original solution by Schwarzschild. You can see that it's not the solution you know at, because, where is that? Okay, you know the R is big R. What is important, the coordinates and angularity. We will see, you know, how difficult it was to understand covariance, regularity, junction conditions. We have to go into the equations. I will not have time to go really in details, but I had to do that. And you will see how complicated it was. And so you see how the Schwarzschild solution, you don't work on the Schwarzschild solution with Schwarzschild's coordinates. Schwarzschild coordinates are here. It was complicated, the reason and so on were complicated. But because it was quasi-polar coordinates for a reason linked to general relativity was not finished at the time when he worked there. But wait, it's not so important. But you have, what you work on is Schwarzschild solution in Drost's coordinates. And Drost was a very important worker in general relativity at the beginning. He was working under Lorentz, and he understood maybe much more precisely general relativity than any others in the 50 years after him, you know. And what is important will be, and I will insist on that, ideology. The Schwarzschild singularity is impenetrable. You cannot cross it. This is a doxa. And everyone will follow it, including Drost. But he understood Drost, only Drost, or quasi-only Drost. He understood that it was something different. He wrote this in his thesis in 1960s. Something different from the Newtonian theory. This was an important point, you know. You will find that quotation in my, okay. Okay, you see, on the proper time. Einstein will insist on the proper time, okay? He will insist in particular, you know, in 1922, I'm going up to the 60s and go on back because, well, it's not so simple. And in 1922, he was invited in Paris, in the Collège de France. And there we had nobody understood relativity, but we had many mathematicians. For example, Langevin understood the special theory, and more probably. But we had Hadamard, great mathematician. We had Pinlevé, a Newtonian one, and he didn't understand nothing, you know. But, you know, he was not alone in the case. Everyone was like him, or quasi anyone. I will tell you what Einstein told him. You have just comments here, you know. Something different here, you know. All points to be reached, and all of that is really a good bon. This is in Paris, and you have, you know, this is Pinlevé. it's pure imagination, you know. The problem is you have many systems of coordinates. You know that better than them and me, maybe. But, well, and how is it possible that the effects be independent of coordinates? This is a simple point he raised, okay? It's pure imagination. The really will be different in different coordinates, okay? He didn't understand. And Einstein, coordinates do not have any physical signification. They do not represent this is really difficult to be understood, you know, because they were Newtonian. And Newtonian, it's the time, the absolute time, and the radial. You know that now, that there is no distance in general relativity. For instance, it doesn't exist when you are up to the theory. And you have the proper time. And that's it. You have to work with that, and it's not simple. Eddington. Bon. Eddington on the Schwarzschild singularity, you will see what he says. Well, he says, you know, it's a magic circle, impenetrable. We'll see how, you know. It's mathematical, just that. An impassable barrier, okay? Just that. But well, why? Well, the Finkelstein is not related to Eddington. This is a legend, you know. It's two different ways. But well, this is important. Hilbert, the great Hilbert, didn't understand relativity. He was not the only one. Even Einstein didn't understand the black hole. I will tell you how he didn't. Einstein, you know, and so, no problem. The problem is, you know, it's a problem of regularity. It's a mathematical problem. He wants the system to be, the transformation of coordinates to be reversible. Of course, if you do that, you will remain, you know, we cannot change really. But why we arrive to Drost coordinates for the solution? It's no reason for that. Now we know that there are others. We'll see that the important paper was due to Lemaitre. Nobody knows it about the Schwarzschild singularity. Nobody read him. It was in French, in an obscure Belgian journal. Okay? But he made many trips to the States, and this was important. Okay? He was a great man. Well, and what Einstein, you know, I have to tell you what Einstein understood that. He says in 1918 in the theta, he worked with the theta, and he understood what the problem was in some way, but he didn't go very long way in this direction. It must exist, a transformation of coordinate, he says. Exist. That was the point, you know. And it didn't ask to be reversible and so on, you know. You are free to choose your system of coordinates and the interpretation. That's our problem, okay? Something like that. Well, I will not be so precise, but the problem of regularity, you know, that's the same as Pinlevé that I told you. If you have a reversible transformation of coordinate, bon, okay, you will stay with the singularity, of course. You have to get a transformation. The first one to say something about that was Lanczos, Cornelius Lanczos in 1922. Alors, where is that? You know, what he made, Lanczos, I remember. He was coming from the Schwarzschild solution, and he found a transformation where, in a point where there were no singularity, he made a transformation and he got a singularity. And so he says, well, it's something there, you know. A singularity is depending on the coordinates. And he understood that, but well, nothing appeared afterwards, okay? He understood something, but it was, you know, it was not a problem. Why it was not a problem? Because I will come back to that if I have time, you know. They knew that 2gm over c square was very small, and there were no objects that could be, at the time, thought to be so dense to exhibit such a field. And so it was not a problem. But it was a problem because, well, they were not, you know, it was something wrong. You will see that. And so I will come on something that I worked much. I work all of paper on trajectories. It's a point trajectories, of course, where you can see what is the space-time really. It was not at the time the idea. The idea was to get the solution and to discuss the solution and to integrate. And they did that in details, not as Giara, which is in any handbook on relativity. Not at Giara, it's not the best. You have many from Drost, De Gens, a Belgian. We made a thesis with De Donder, and it was all of a collection of works on trajectories. Every trajectory is integrated from the beginning in, you know, the problem is that the Schwarzschild solution, it's a general exact solution. On the trajectories, you can integrate them in detail with, you know, the Weierstrass solutions and so on, equations, and you can get all the solutions in detailed and exact. And so you can see what appeared, how it works. And they did that. Okay, trajectories. See that? You see? It's all okay, but well, what's the problem? The problem is with the time, always, you know. The time, the Newtonian time, the coordinate time t, they will always come back to the time coordinate t, always. Well, it's really a pity. Why? You know, see at Drost on the radial fall, I will speak on the radial fall because, you know, it's Galileo's problem. You see, what he defined, a physical distance, you know, it's always the point. When I was young, I saw people in where I worked. They were working on rigidity, on physical distance, and so on, to define something which was not, you know, the time. And, wow. It was bon. You know, see at what he says, from the integration, and he understood that it was something different, but well, you know. We don't not consider the space alpha is 2gm over Earth over c square. Okay, that's the way they wrote it. The particle will never reach the sphere. The moving particle out of the sphere will never get into it. Infinite time to get to the singularity. Okay, and this, it will be, you know, the representation they accepted. Everyone. Ah, there is. For once, this result is for once different. This is important, because people didn't say that. Only him, okay, before the 60s, okay. It was, look at, this is De Gens, an excellent thesis, a work without any failure. Everything, I did the calculations, you know. It was splendid. Alpha is, of course, you know, the whole, you know, it's a hole in it. You don't enter. You don't, you cannot. And it's what Eddington said, a magical sphere. The light will, you know, will be there on the singularity or something like that, but they were not interested really. He is not the only one, you will see. Hilbert, the same. Lauer, the same. See that? Lauer from Hilbert 1917. You know, look at. All of that has been done very well, but well, you do not enter. You know, you put that on your mind. It's worse. I have looked at the equations, radial fall, but also the phi parametrized. When you are in phi, you know, like here, you enter. The equations enter. They cannot see it. The equation says you. No problem. The radial fall, when you take the proper time for the radial fall, it's the same solution as the Newtonian one. The same. Maybe I have the equation there. No? Ah, yes, it is here. Okay. Newtonian equations, but in proper time. And they see that. Many. But well, you haven't. And they came to the T, they take the second equation there in order to have the singularity. We need it in order not to enter, because my boss said, you don't enter there. It's ideology. The equation said, same equations, the proper time, Einstein says, it's important. Everyone, you know, it's always like that. Not only in history of science, you know, so ideology is important. If you publish something different, even if it's genial, maybe it will not be accepted, your paper. It arrives, you know, often. But well, that's like that, you know, because it's in institutions. And so it's not only mathematics, it's always in their head, you know, in their brain. They don't accept, okay, my boss says, okay, and this is clear. For example, it's just an example because there are many. Rab, it's a colleague of yours, a German astronomer. He did that. He found it, and it's in 48, I think, okay? And he goes to T, the Newtonian time. No problem, okay? No problem. Now we come to the new way. I told you that Langschuss, you have here the equation of singularity that he made to appear in order to prove that the singularity could be, you know, dependent of the coordinates. Okay? It's in R equal m. Okay? It may be possible to remove the letter by coordinate transformation. Okay? Let's come to Lemaitre. Really, it's much more important than you can say, understand. Say, no. Einstein with Lemaitre. And there, well, I will not enter the equations, but it's necessary. What he did, it's simple. He was a cosmologist, everyone knows. He was interested on, you know, in homogeneities, and he wanted to mix Schwarzschild. I'm really going very fast, you know. It's much more complicated. I have only 40 minutes to tell you all of that. It's really a very important work by Lemaitre. And he wanted to get, you know, in homogeneity in a cosmological universe. Okay? And how he reached it? You know, everyone knows the Bondi solution. The pressure is zero, you know, a null pressure solution. It's Bondi, it's Tolman, never Lemaitre, but it's Lemaitre. It's Lemaitre who discussed that with Tolman and to America, to Oppenheimer. That's the real. Why? Because in the null pressure solution, you will have Schwarzschild exterior solution, Schwarzschild interior solution, Friedmann solution, and so what he will do? But well, he has no complex. Einstein didn't like very much Lemaitre, everyone knows, the way he handled the theory. But he was better than Einstein on this side, okay? And what he did? He took the Friedmann solution, made a cutoff, just a sphere, you know, representing a star. You are not obliged to have all the cosmology. You have just, it's the interior solution. Schwarzschild's interior solution, but dependent on T, you know. with null pressure. It's not exactly Schwarzschild, but well, you know, you understand that it's simple. And you put it, and you have the Schwarzschild solution. And so you know that there is no singularity in a Friedman solution. And it's no problem when you collapse. He did that. He thought it. And he showed it mathematically in this, and well, and they were complicated this year, but well, it has to be done, but now it's clear, you know, you can come to this solution. The Bondy solution, Bondy didn't do anything, but he didn't know as well Lemaitre, an obscure journal in French, you know, for Austrian people. It's impossible. But it was always like that in relativity. Everything has been done 1, 2, 3 times. Okay, but well, it's not a problem. It's a problem of relativists. They were in many places to work on relativity, and they had no connection. The importance of Lemaitre, too, was to go to the States, to Canada, to discuss with the people there. And he did that, you know. He wasn't one of the first. Einstein was coming too, but he was just to present Einstein and the deviation of light, not to work with people this way. He was really working afterwards in Princeton with Bergman. We will speak on Einstein. How much time I have still? 15 minutes? Yeah? 7 minutes, okay. Okay. And so, I was on Lemaitre, and he wrote it, that the Schwarzschild singularity, I should have it there, the equation. This is what? The equation of the Friedman solution in which, you see, this contradicts the generally accepted results that a given mass cannot have a radius smaller than 2gm. This is the important point. And afterwards, of course, the singularity is fictitious. But well, we are in 32, 33, and we have to wait quite a long time after the 60s to understand that. You know how complicated it was, okay? But he was going. This is Tolman. Tolman wrote a paper in 1933-4, I don't remember, no problem, a very good book at the time on thermodynamics and relativity. And he discussed much with Lemaitre when Lemaitre came to the States very early. He made a thesis in MIT, and then he came in 1925. He came back in 1927, worked with Vallarta. Vallarta was an assistant of Einstein. And after that, he came back in the years 32, 33, when he wrote this solution, you know. And he discussed with Tolman. He worked with Tolman. He saw Robertson. Robertson, you know that, you know, as a name, but he worked very much on this. I will go fast. Okay, this is Lemaitre, and now, Einstein has a radial fall. Just he wrote a paper in 1939, the same year as Oppenheimer and Snyder, the important paper. We will have a look to it, but generally very fast. And well, what he did, there is no problem, the singularity is singular. Why? You know how he handled? He take circular orbits for all the matter. And everyone knew that there didn't exist any circular trajectory because only if the radius is greater than 3m. And so it was just, when he began working on that, here's the result. It couldn't cross the singularity. When you don't want it to fall in, you don't take radial fall. This is clear, you know, in your mind. It takes circular motions. The paper is zero. It's one of the worst of Einstein. That's it. he worked with Bergman, who translated, and Bergman as well didn't understand, and Peter Bergman didn't understand that. There were more mathematicians than physicists in some way. Even Einstein, in some way. Okay, and so it's a very bad paper. I wrote all of a paper with John Herman on that. Einstein and singularities from the theater, all of it. But well, you know, it was not accepted at first, and he had to publish it, I don't know where, but he published it in Annals of Mathematics. It was a mathematical. But well, he worked by Robertson. Robertson at Fine Hall in Princeton. And there, Robertson, a great cosmologist everyone knows, was interested in the point. But Einstein didn't understand his point. Okay. And let's come to Robertson. You have that, you know, the radius. 2GM is very small. This is in the book. He didn't publish anything before he died. I think he died in 61 or something like that. Yes, he was young still. And he didn't publish anything, but he gave lectures and sing the great things, the mathematicians. I love him. He didn't understand everything, but and he was good. We will have just 2 minutes to look at Singe. But, you know, what he did, he read Le Maître, because he didn't publish anything, but Noonan, his assistant, after he died in 68, published notes of his lectures. And it has been published, you have it in the libraries. And you can see how far he is. I think that he's going further on than Oppenheimer, because he's going in, you will see, just. Look at, you know, outgoing and ingoing. 2M here. 1 is 2M, it's the horizon. Now, maybe we can speak of an horizon. These are incoming. The problem now is topology. Clear? But there, well, it's complicated. The same from Robertson and Noonan. And it's come from Le Maître. He quotes at Le Maître. And he is not the only one. You know, see that? The particle passes and reaches in a finite proper time. That's the first time. Even further on than Le Maître. Okay? Because he's collapsed, speaking. Let's come to Singe. You know, he did a very good paper in 1950 before Kruskal. This is Oppenheimer and Snyder, everyone knows. I will not insist on that. You have here Kruskal and Singe. You know, you see, you know, it's important. I didn't work so much on that. It has to be done, but you know, there are so few historians of relativity, and generally they are not really, as far as I know, interested in that. It's a pity, but well. And now let's come to the end of what I can tell you. You know, you have 3 cosmologists, Le Maître, Robertson, Tolman. And Tolman wrote a paper on the inhomogeneity and so on. He was interested in quartet at Le Maître. But well, he was really important that way. And cosmology had always been, you know, important for general relativity. Look at what said Oppenheimer, you know. In the 40 years that have elapsed, you know, their connection between the general theory and experience were slender, all the same as Born, you know, it was Born. But the exception lays in the field of cosmology, you know. And this, why? Because in cosmology you have not to work on a very small object where curvature, and didn't speak of curvature, you know, is important. It's impossible to realize that, you know. It's really important. And so in cosmology, you have more free, you know. You can, and cosmology, I wrote a paper, is a space of thought in general relativity. It's really the, you know, the way where relativity could have a breath, okay? But not in the neo-Newtonian interpretation, which was important because, well, it worked out. I don't say that it's nothing, no, but well. Bon. Conclusion. Bon, I have to tell you just a word on something. Maybe some of you heard of dark bodies. Dark bodies. It was after Newton by a man named John Mitchell. And Laplace, everyone, it's in any book in relativity, you know, but they didn't look at the papers. But I did, I was really interested in that. And so dark bodies are the cousins of black holes, okay? And I looked at that, and you have to know that in 1922, Lennart here in Berlin, he was an anti-Semitic, and he was looking at a paper by Soldner in 1801, where, you know, the deflection of light appeared already. And you say, well, it's not Einstein, it's Soldner, always the same. Okay, but what? Soldner did the calculation in the same context as Mitchell. And this is in Newton in the Principia. In the Principia, and it's all that what I worked on after when I left this field. You know, you have all of that. You have Newton, you have Clairaut, a French, Soldner, you have Arago, and here you have Blair. I have nothing from, well, there are many people working. What's that? It's a Newtonian theory of the propagation of light. And what they did, it's simple, what I was long to understand, because nobody worked on that. It was a forgotten theory, but a theory. What they did, they took corpuscle of light as material corpuscles. You know, you take a corpuscle like the planets, because it's corpuscular, and Einstein is also a corpuscular theory, look at. And it's light and gravitation, and they make a light material corpuscle, fast as light, and what appeared? Everything. But the perihelion, the deviation of light, the dark bodies, even, you know, the redshift, and it's not me, it's in the papers, okay? I found the papers where it was done. And the Doppler effect, before Doppler. Doppler has done nothing, you know, nothing, only for sound, not for light. And before Doppler, it's Blair. He is not known, unknown astronomer. And so I've worked on this side afterwards because I wanted to shift from relativity and hoping that someone will go further on the topological interpretation that I didn't work on in details. So thank you for your attention and for the invitation, Bernard.
Thank you very much for such a fascinating review and insight into things. There are several of those things I didn't know about in the development of relativity in the 20s and 30s.